Thank you very much for the introduction. So I'm Frans. I'm going to talk about Spade, and of course we need to motivate things. So my motivation is very much in line with the answer to my question. It's abstraction, and to me this is sort of saying what things we have to think about and what things we are in control over. So as an example, you have Verilog and VHDL. They are going to be low level in almost any way you look at them, but you can do low level Verilog and sort of instantiate individual AND gates in a netlist, or do high level Verilog, doing more behavioral description and reasoning about sort of individual operations on individual bundles of bits. On the other end of the spectrum, we have high level synthesis. Here we've given up a whole lot of control, but we also have way less things to think about. Now, Spade is absolutely not a high-level synthesis tool. Just like BlueSpec, it falls on the lower end side of the spectrum. And the goal with everything I'm trying to do here is to retain the control that you have with Verilog and VHDL, but push the amount of high-level reasoning you can do while still retaining that control. So first of all, I want to give I also want to steal a bunch of stuff from software languages, because I'm a software developer, and I miss a lot of things when I come to Verilog and VHDL and other HDLs. So I want to start off with an example of what the language looks like. This is sort of the hello world, a counter that counts from some value, or from 0 up to some maximum value. The inputs are separated from the outputs. So yeah, here we take a clock reset and a max value, and this thing produces a current counter value. And the whole language is more linear than Verilog and VHDL, for better or for worse. But I think it's easier to reason about things in a linear way and then explicitly do non-linear flow of data, I suppose. To define a counter, we need a register. We call that register val, and we clock it by this CLK signal. The register statement is the only sequential statement in the language. Everything else is combinational. We specify a reset, so if the RSD signal is true, then we set it to 0. And then to describe the behavior of the circuit, we give a new value of the register as a function of the old values. So if the current value is at the max value, the new value will be set to 0. Otherwise, it will be the old value incremented by 1. Some key takeaways here. First of all, it's an expression-based language. So instead of saying if val is max, set val to 0, we say val is the result of this if statement, and then we have to specify a value in each branch. And that prevents a few bugs, and once you get used to it, I think it's a more natural mapping to hardware than the imperative style that most HDLs have. It's a statically typed language, so we specify all the types. It also tries to make sure that you don't accidentally throw away information that you might need. So if you do val plus 1, that could overflow, so the language will not allow you to throw away that overflow implicitly. You have to call this trunk function to say that, no, I actually do want to throw away a bit here, since we have a feedback in the circuit. It has type inference, so you don't have to specify any types inside the body. The compiler figures them out for you. As long as things are fine. If the compiler finds some inconsistency, then it will, of course, alert you. So you get the benefits of static types without the annoying typing. And unlike BlueSpec, this is a cycle-to-cycle description of your hardware. You give the new value of all the registers as a function of the old value of all the registers, but you have a lot more structured tools for doing this than you do in Verilog and VHDL. One of those tools that you have access to is a pipelining feature. So on the left here, you have some code. On the right, we have the resulting hardware. The thing I want you to pay attention to is these 3 lines. So first of all, the head of the pipeline specifies its latency. So just by reading the head, you can now see that the delay between input and output in this module is going to be 2. Then you have the 2 reg statements, which specify that all the variables above a reg statement should now be registered, and when you refer to those variables below the reg statement, refer to the register version. And this decouples the description of where you put pipeline registers from the computation that you're performing inside the circuit. This is useful when you're describing the circuit originally, but it's way more useful when you have to refactor things. So let's say we realize that this G block at the top is too slow. It's breaking our Fmax, so we need to optimize it. And we do that by pipelining it. And normally you would have to do a bunch of thinking now, like what do I have to change because of this? In Spade, because the compiler knows about pipelines, it will first tell you that, hey, you first need to instantiate this G block as a pipeline. And you specify the depth there, so if there was more complex behavior here, the user would need to go back and check that, okay, there is no, either change the circuit to match a new description yeah. If in this case, the compiler will actually figure out the problem for us. We have this line going backwards through the pipeline. The behavior of our circuit changed, so the compiler will tell us that this X value is not available where you're trying to use it. You need to use it in a later stage. Of course, the solution here is to delay the computation of this whole pipeline one cycle. So we insert these two registers, these two new registers into the pipeline, and because we decouple the description of pipelining from the description of the computation, the only change we have to make is to put reg there and update the depth of the outer pipeline, because now that changed the latency of the pipeline. This pipelining feature has a few more things that I don't have time to go into. You can do feedback and bypasses, so you can say, I want to refer to the value of this register 2 cycles ago, or 2 cycles in the value as it appears in two stages below me, for example. This is very useful if you're doing something like a processor where you have a register file that is sort of feedbacks on itself. You can also do, as of a few weeks ago, you can do, there's some built-in support for dynamic behavior, so you can say that all of the stages here should, or all the pipeline registers in this stage should stall if a condition holds, and then it will stall all the pipeline stages above this. And this allows you to do correct flushing, and there's almost enough support in the language now for doing back pressure negotiation between the pipelines, so you can solve that as well in a structured manner. That's the pipelining construct. One of the things I wanted to steal from software languages was the type system. So one of the major things I miss in a lot of languages that don't have this is the enum, and the more powerful enum in the Rust sense rather than the enum of C, where it's just one of a set of values. The type system supports generics, so we define a type here called option, and it's going to be generic over any type T. We could put integers in there, we could put structs in there, other enums, whatever we feel like. You can, this option type will take on one of two values. Either it's some, in which case a value is present, or it could be none, in which case no value is present. The best way to view this to me is as a valid bit that is bundled with the data it validates. So the representation of this type will be a tag along with a value. If the tag is 0, the option type is none, and the value bits are undefined. And we're not going to be allowed to access these bits unless we first check that the tag is 1, in which case the compiler will give us access to the bits. So this prevents reading data that wasn't really valid. This is very useful for a lot of other things as well. You could model commands on a bus. For example, if you have a memory, you could have no operation on the memory, you could have a read operation, or you could have a write operation, and you can bundle the data that it needs. You can model an instruction set. So you have a set instruction where you have a destination register and an immediate value. You have an add instruction where you have a destination register and two input registers. Or you can have a jump instruction, which is a target. And this will be encoded in a similar way. And it's very nice to match on these, and then you only get access to the fields of your instruction that you actually have a use for. Finally, tooling. I think tooling is a very important part of any language. I showed briefly the compiler error message. That's something I'm very passionate about. The compiler should give you useful error messages that describe what you need to change to make things work. So any bad error, any unclear compiler error message I consider a bug. We have test batches in CocoDB, and CocoDB is a Python testing framework for Verilog. The thing that Spade appends to it is the ability to write Spade code inside CocoDB. So you can write a string with a Spade expression, it goes out to the compiler, compiles it, and that way you don't have to care how the compiler decided to encode your enum or your struct. And there's a build tool. So it can manage dependencies. Here I say I want a RISC-V implementation, and the from a path and a RGB LED driver from some Git repo. It can call build tools for you, so uses an XPNR, and it's scriptable via plugins. So this specifies that I want to bring in a plugin that generates a program memory for an assembly file, from an assembly file. And the last slide, Spade is an open source project. Of course, this is OSDA. It's implemented in Rust, but it's not using any of the Rust compiler. It's not embedded inside Rust. It is a standalone language. It's just that I take a lot of inspiration from it and implemented the compiler in Rust. It's targeting Verilog, which is not great. It's easy to do, and all the tools support it, so that's why I decided to do it. But I would like to explore something else like Circuit, Calyx, or RTLIL, because that would give me a whole lot more nice features. That's all I had to say. If you want to learn more, there's a website, spadelang.org, or you can follow me on Mastodon, where I ramble about this language. About this language.
Very good. Thank you very much, Frans. So, questions?
I'm trying to grasp how this fits into your first diagram of the varying levels of abstraction. How would you compare its capabilities with something like Chisel or like this?
Yeah. For Chisel, I actually have a slide because I get asked this question a lot. So, of course, Spade is a new language. It's Chisel and all the other languages are going to be way more mature. I would say all of the languages kind of push the abstraction level, but Chisel in particular, and well, I guess Chisel and all the other sort of hardware construction languages, as I think they call them, they do so by doing metaprogramming. But when you can't use metaprogramming, when you're describing the individual sort of operations that you want to perform, you're still doing sort of bundles of bits and individual operations on those bundles of bits. So there's no pipelining feature because it's just bundles of bits. You don't have any nice types at the hardware level. You don't have this pattern matching that you can do on the enums. I didn't show that off due to time, but and they're also imperative. So I think you have this, if this happens, set this, which I think is sort of the wrong way to view hardware. And they're also embedded languages. So to me, they feel kind of clunky. You have to do when, else, when, otherwise instead of if, else, which is fine, but then the auto formatter kind of messes with it when you do that. And yeah, there's some other stuff as well. You can read the points on the slide. But I hope that answers the question. You asked about LiteX as well? Or?
Which is in the same space.
Yeah. Yeah.
Could you give us an example of what you or others have designed with this?
Sure, yeah. So it's kind of early stages still. I have a working RISC-V processor, a 5-stage pipeline thing that it only supports the base instruction set for now. I've built the controller for a research project I'm working on, which is sort of doing dynamic programming. So it's feeding a bunch of stuff into a long pipeline and writing the results back to memories. I'm playing around with talking to SDRAM now. So for that I realized that I don't really want to write a SDRAM controller right now. So then it's more like, can I integrate light DRAM with Spade in a nice way? And some random games. A few friends of mine and I built a game during a game jam. So
I've used, I guess, the MyJet, which is the older version of camera,
yep.
a lot. And I guess your work because I spend hours just wasting time trying to figure out typing-related issues.
Yeah.
So I do it.
Nice, thanks.
And I also love Rust, which is nice to see. The only thing is how much could you push this sort of train of thought of basically leveraging typing and like Rust-like tightness, but which comes with a lot of relief that you sort of gain over time. But at the same time, how much frustration has it been in terms of like trying to put things in that way? Has it been a positive journey, and how do you feel about it?
I've had lots of fun with this project. I started it like 2 years ago as a hobby project, and then it turned into a work project, and I still find it super fun to work on. So it's a fun challenge. It's nice to have things to like borrow from with your typing thing. A thing that isn't a thing in software, but is a thing in hardware, is like modeling ports. So I didn't get into that here, but I have a system for similar to the lifetimes in Rust, but for modeling so that you can only use a memory port, for example, once. If you try to give a memory port to two different independent circuits, the compiler would say like, no, it's being used twice.
Okay. Yeah, that seems to me going a bit heavily on the Rust side. I do enjoy the fact that like when I use MyGen or it's a Python-based thing, and you have this introspection into the objects. Mm-hmm. You can actually, there's a lot of power being harnessed there.
Yeah.
Unfortunately, there's not enough strict typing, which I think is coming in Python, but at the same time.
Yeah.
So there's a trade-off to be had there. I think there's expression and ease of expression.
Yeah. Yeah, I'm very much on the typing side of things. So.
Yeah, actually, I could follow up on that also. So, as I mentioned in my talk, we use essentially all of Haskell's type systems, not a subset of Haskell's type systems, but in use that, and we are just complete firm believers of that. But there are all kinds of interesting, apart from just general matching types and making sure you can parameterize the polymorphic types, there are other aspects that you get out of that that are really beneficial. So, for example, in Haskell, you have a concept in the type system called type classes. And it's a kind of a very disciplined, structured form of overload. And when you do that, what you can do is, for example, in the examples that he gave a little earlier on the enum and the struct, there's two separate questions. One is logically, what is the enum and what is the struct? And then the other is physically, how do you represent that in bits? One way to do it is a particular tagging scheme this way or another tagging scheme that way. Type classes completely solve that problem. You can separate out the concept of logically what is the enum and the struct versus what the representation is. That's one example of type classes. Another kind of place where you use type classes is if you think of a large system that has control and status registers floating all over the place in different modules. Ultimately, that's a global space of control and status registers, and plumbing it through module interface is often extremely messy. Yeah. Again, type classes completely solve that problem for you because you can hide the plumbing using the monadic type that you have. So we're just complete believers in very strong polymorphic typing in hardware design languages.
I agree.
Thanks for the discussion. Are there more questions?
Just one question. How did you choose pipelining, that the user specified pipeline, not latency? Like in some HLS tools, you specify latency, and the tool will do the retiming for you.
Yeah. The answer is I want control of the retiming, I guess. So the reason I started this project was I was doing a bunch of pipelining stuff, and then if you're doing it in Verilog, you do _S1, _S2, and then you have to make sure you refer to things. And I still wanted that level of description. I just didn't have to do it. I didn't want to do the work manually because it seemed so easy to automate. So if you want more, like you specify a latency and it does the retiming for you, you should look at pipeline C, which is also another HDL, and it does this iterative retiming automatically.
Okay, thank you.
Great, thank you. So you're in the middle of the coffee break. Thank you so much, Frans, for your